Hey guys, today we're going to talk about gas exchange and transport. Welcome to another episode of the Human AI podcast. I'm here with an AI, Grok. It's going to be explaining to us today's topic. Please take everything it says with a pinch of salt. Let's start. So, Grok, introduce us to today's topic.
All right, let's dive into gas exchange and transport. In humans, this is all about how oxygen gets into your body and carbon dioxide gets out. It starts in the lungs, where air hits tiny sacs called alveoli. Oxygen diffuses across their thin walls into the bloodstream, binding to hemoglobin and red blood cells. Meanwhile, carbon dioxide, a waste product from your cells, moves from the blood into the alveoli and gets exhaled. The heart pumps oxygen-rich blood to tissues, where cells use it for energy, producing carbon dioxide that's carried back to the lungs. It's a non-stop cycle, super efficient, but things like lung diseases or low oxygen environments can mess it up. Want me to zoom in on any part of that?
Tell me about the blood-gas interface and about Fick's law, which might help us understand what we're talking about.
The blood-gas interface is where gas exchange happens in the lungs, specifically in the alveoli. These tiny air sacs have super thin walls, allowing oxygen to diffuse from the air into the blood and capillaries, while carbon dioxide moves the opposite way to be exhaled. The interface is efficient because of its massive surface area, about 70 square meters, and the close contact between air and blood. Fick's law explains how this diffusion works. It says the rate of gas movement depends on three things: the surface area of the interface, the difference in gas concentration between air and blood, and how easily the gas passes through the membrane. A bigger area, a steeper concentration gradient, or a thinner membrane speeds up diffusion. For example, oxygen moves faster into the blood when you're low on it, like during exercise. Anything else you want to dig into?
Let's talk about Fick's law a bit more. So, basically, we can understand through it that the rate of diffusion is going to be proportional to the surface area and to the concentration difference. And it's going to be inversely proportional to the thickness of the membrane. What does it mean for it to be proportional to the concentration difference?
All right, let's zoom in on Fick's law and that concentration difference part. When we say the rate of diffusion is proportional to the concentration difference, it means the bigger the gap in gas concentration between two areas, like the air in the alveoli and the blood in the capillaries, the faster the gas moves. For example, if the oxygen level is high in the alveoli, but low in the blood, oxygen rushes in quickly to balance things out. It's like water flowing faster down a steeper hill. This gradient drives diffusion, so during exercise, when your blood's oxygen drops, that bigger difference speeds up oxygen transfer into the blood. Clear, or want me to break it down more?
No, that makes sense. So, pulmonary blood vessels form a series of branching tubes. And explain us how this structure looks like. And so, tell me about the capillaries and how they form a dense network and how this relates to gas exchange.
The pulmonary blood vessels start with the pulmonary artery, which carries deoxygenated blood from the heart to the lungs. This artery splits into smaller branches, forming a tree-like network of progressively smaller tubes, arterioles, that spread throughout the lung tissue. These eventually lead to the capillaries, which form a dense, web-like network surrounding the alveoli, those tiny air sacs where gas exchange happens. The capillaries are super thin, with walls just one cell thick, maximizing contact with the alveoli for efficient oxygen and carbon dioxide exchange. This dense network increases the surface area, huge, like a tennis court is stretched out, which, per Fick's law, boosts diffusion rate by giving more space for gas molecules to move across. The setup ensures oxygen rapidly enters the blood and carbon dioxide exits, keeping the process fast and effective. Want me to clarify any part of that structure or its role?
That's all good. I would like to ask you a bit about the alveolar gas equation now.
The alveolar gas equation helps us figure out the partial pressure of oxygen in the alveoli, which drives oxygen diffusion into the blood. It's roughly PaO2, PiO2 minus PiCO2 R, where PaO2 is the alveolar oxygen pressure, PiCO2 is the inspired oxygen pressure, PaCO2 is the alveolar carbon dioxide pressure, and R is the respiratory exchange ratio, usually around 0.8. In simple terms, it tells us how much oxygen is available in the alveoli for gas exchange after accounting for carbon dioxide. For example, at sea level, inspired oxygen is about 150 millimeters of mercury, and if CO2 in the alveoli is 40 millimeters of mercury, the equation estimates PaO2 around 100 millimeters of mercury. This matters because a higher PaO2 means more oxygen can diffuse into the blood. Want me to explain
So
any
who
part of
made
the...
this equation? It's quite a peculiar one.
Yeah, the alveolar gas equation is a bit unique, isn't it? It's like a snapshot of what's happening with oxygen in the alveoli, balancing the oxygen you breathe in against the carbon dioxide you're kicking out. The weird part is how it simplifies a complex process into something we can calculate, showing how much oxygen is actually ready to jump into the blood. That respiratory exchange ratio, usually 0.8, is a cool fudge factor. It accounts for the fact that we produce a bit less CO2 than the oxygen we use. If you want, I can walk through a quick example with numbers to
Yeah,
show
I
how...
don't understand it, dude. Honestly, I don't understand it. So, what is PaO2? So, what is that symbol? And what does fractional inspired oxygen have to do with it? Why do we times the fractional inspired oxygen with Pi and we minus the PH2O? Why do they... Like, I don't understand even one step. So, break it down, like...
All right, let's break the alveolar gas equation down step by step. Super simple, like we're chatting it out. The equation is about finding PaO2, which is the partial pressure of oxygen in the alveoli. Basically, how much oxygen is available in those lung air sacs to move into your blood. Let's go through it piece by piece. First, PaO2 isn't the same as PiO2. PaO2 is the oxygen pressure in the alveoli, while PaO2 is the oxygen pressure in arterial blood after it leaves the lungs. We're focusing on PaO2 here, as it sets up how much oxygen can get into the blood. The equation is PaO2 plus PiO2 minus PaCOR. Let's unpack each part. 1. PaO2, inspired oxygen pressure. This is the pressure of oxygen in the air.
So we have the partial pressure of oxygen in the alveoli. What is fractional inspired oxygen, fractional concentration of oxygen?
All right, let's clear this up. Fractional inspired oxygen, or FiO2, is just the percentage of oxygen in the air you breathe in. It's a simple way to say how much of the air is oxygen versus other gases like nitrogen.
Well, wait, I thought this is what partial pressure means.
I hear you. It's easy to mix up fractional inspired oxygen, FiO2, and partial pressure. They're related, but not the same. FiO2 is the percentage of oxygen in the air you breathe in, like 21% in normal air. Partial pressure, like PaO2, is the actual pressure that oxygen contributes within the total air pressure. Think of it this way. FiO2...
One has to do with pressure, the other has to do with, like, amount.
Exactly, you're getting it.
But wait a sec. How does air cause pressure?
Great question. Air causes pressure because it's made of molecules, like oxygen and nitrogen, that are constantly moving and bouncing off surfaces, including your lungs. This movement creates a force per unit area, which we call pressure. In the context of breathing, the total air pressure in the atmosphere, about 760 millimeters of mercury at sea level, is the sum of the pressures from all gases in the air. Each gas, like oxygen, contributes its own share, called partial pressure. For example, since oxygen is 21% of air, FiO2 is 0.21, its partial pressure in inspired air before it hits the lungs is roughly 0.21 times 760, which is 1,000 millimeters of mercury. But in the lungs, water vapor and other factors tweak this number, which is where the alveolar gas equation comes in. Want me to tie this back to the equation or keep digging into pressure?
Well, so why do we times the fractional concentration of oxygen with the pressure of inspired air minus the partial pressure of water?
All right, let's clear this up. In the alveolar gas equation, we calculate the inspired oxygen pressure, PiO2, by taking the fractional concentration of oxygen, FiO2. That's the percentage of oxygen in the air, like 0.21 for room air, and multiplying it by the total atmospheric pressure, minus the water vapor pressure. Here's why. When you breathe in, the air enters your lungs, but it gets humidified by water vapor in your airways. This water vapor takes up some space, adding its own pressure, typically about 47 millimeters of mercury at body temperature. So, to find the actual pressure of oxygen in the mix, you take the total air pressure, say 760 millimeters of sea level, subtract the water vapor pressure, 760 minus 47 equals 713 millimeters of sea level, and then multiply by FiO2. 0.21 times 713 actually equals 150 millimeters of sea level. This gives you PiO2, the starting point for oxygen in the lungs, before other factors like CO2 come into play in the equation. Makes sense? Or want me to walk through it again?
So we minus the water because something to do with vapor. I don't know why we times it though.
Yeah, you're on the right track. We subtract the water vapor pressure because when you breathe in, the air gets humidified in your airways, and that water vapor adds its own pressure, about 47 millimeters of sea level. This takes up space, so it reduces the effective pressure of the other gases, like oxygen, in the mix. That's why we take the total atmospheric pressure, say 760 millimeters of sea level, and subtract the water vapor pressure, 760 minus 47 equals 713 millimeters of sea level, and then multiply by FiO2. Now, why do we multiply by FiO2, the fractional concentration of oxygen? Because FiO2, 0.21 for room air, tells us what portion of that remaining pressure comes from oxygen. So, 0.21 times 713 gives us roughly 150 millimeters of sea level.
And what does RQ, what does the respiratory quotient mean, and why do we throw that in the equation too?
The respiratory quotient, or RQ, is a ratio that shows how much carbon dioxide, CO2, your body produces compared to the oxygen, O2, it uses during metabolism. It's typically around 0.8 for a normal diet, meaning you produce about 0.8 molecules of CO2 for every molecule of O2 consumed. In the alveolar gas equation, PaO2 equals PiO2 minus PaCO2 plus RQ minus PaCO2 plus R. We include RQ because it accounts for the exchange of these gases in the lungs. The PaCO2, the partial pressure of CO2 in the alveoli, affects how much oxygen can stay in the alveoli. Dividing PaCO2 by RQ adjusts for the fact that CO2 production and O2 consumption aren't always equal, depending on what your body's burning, like carbs, RQ addict 1, or fats, RQ addict 0.7. This keeps the equation accurate for calculating the alveolar oxygen pressure, PaO2. Want me to run through an example to show how RQ fits in?
So, tell me, with the respiratory quotient, dude, to be honest, I'm having real trouble understanding this equation in general. Could you explain it really simply to us? And why it's so important, like, to understand gas exchange and transport?
Alright, let's make the alveolar gas equation super simple, like I'm explaining it to a friend over coffee. The equation's job is to tell us how much oxygen is in the alveoli, those tiny lung air sacs, ready to jump into your blood. Why is that a big deal? Because that oxygen level determines how well your body gets the oxygen it needs for energy, and how efficiently it dumps carbon dioxide, the waste gas. If this process messes up, you're not fueling your cells right, and that's bad news, like trying to run a car with a clogged fuel line. Here's the equation, broken down plain and simple. PaO2 equals PiO2 minus PaCO2 plus RQ minus PaCO2 plus RQ minus R. Don't worry about the letters yet. Let's just walk through it. 1. PaO2. This is the pressure of oxygen in the alveoli. Higher pressure means more oxygen available to enter your blood. Think of it as the oxygen ready to go in your lungs. 2. PaO2. This is the pressure of oxygen in the air you breathe in, but adjusted for your lungs. You start with the oxygen in the air, about 21% of it. That's FiO2, or 0.21. At sea level, total air pressure is 760 millimeters of air, but your lungs add water vapor, like humidity, which takes up space, about 47 millimeters of sea level. So, you take 760 minus 47 equals 713 millimeters of sea level. Then, multiply by 0.21 to get PaO2, about 150 millimeters of sea level. That's the oxygen pressure you're starting with. 3.
Why are we minusing PaCO2 over RQ from the rest of the FiO2 times Pi minus PH2O? Answer to me in 2 sentences.
We subtract PaCO2RQ in the alveolar gas equation because the carbon dioxide, PaCO2, in the alveoli takes up space, reducing the oxygen pressure available for diffusion. Dividing by the respiratory quotient, RQ, adjusts for the ratio of CO2 produced to oxygen consumed, ensuring the equation accurately reflects how much oxygen, PaO2, is
Okay,
left.
that's a good answer. And in 2 sentences, why do we divide the PaCO2 with RQ?
We divide PaCO2 by RQ in the alveolar gas equation to account for the ratio of carbon dioxide produced to oxygen consumed during metabolism, which varies with diet or activity. This adjustment ensures the equation accurately calculates the oxygen pressure available in the alveoli for gas exchange.
This is not a sufficient answer, because you don't relate it to the rest of the equation. Why do we divide it? Our goal is to find the partial pressure of oxygen in the alveoli. Why would we divide the respiratory quotient over the PaCO2? I understand why we will minus the PaCO2. You explain, it takes up space.
All right, let's zero in on why we divide
2
PaCO2.
sentences, 2 sentences only.
We divide PaCO2 by RQ in the alveolar gas equation because RQ reflects the ratio of CO2 produced to O2 consumed, adjusting the CO2's impact on alveolar oxygen pressure. This ensures PaO2, the oxygen available for diffusion, is calculated accurately by accounting for metabolic gas exchange differences.
Yeah, but why would we divide the PaCO2 with the RQ? Why does it fit? I understand that it's the ratio of the CO2 consumed and the oxygen, the CO2 produced and the oxygen consumed. I don't understand how it fits in the equation. Why it needs to be there. Answer to me in 1 sentence.
We divide divide PaCO2 by RQ in the alveolar gas equation because RQ adjusts the CO2 pressure's impact on oxygen availability, ensuring PaO2 reflects the true oxygen pressure in the alveoli by accounting for the metabolic balance between CO2 production and oxygen consumption.
All right. I didn't understand, guys, but I want to keep this episode short. Maybe we can do a deep dive on it another time. Let's talk about the AA gradient now. So, what's the AA gradient, and how can the alveolar gas equation help us find the AA gradient?
The AA gradient is the difference between the oxygen pressure in the alveoli, PaO2, and the oxygen pressure in arterial blood, PaO2. The alveolar gas equation helps calculate PaO2, which we compare to PaO2 measured via blood tests to find the gradient, revealing how efficiently oxygen moves from lungs to blood.
And is it alveolar minus arterial or the other way around?
It's alveolar minus arterial, so the AA gradient is calculated as PaO2, alveolar oxygen pressure, minus PaO2, arterial oxygen pressure.
Okay. And so let's say, so tell us how the alveolar arterial gradient might show that something is going wrong. Is it if it's too steep? Is it if it's too horizontal?
A steep or widened AA gradient, meaning a big difference between alveolar oxygen, PaO2, and arterial oxygen, PaO2, signals something's wrong, like lung disease or poor gas exchange, because oxygen isn't moving efficiently from the alveoli to the blood. If the gradient is too small or horizontal, close to normal, around 10-20 millimeters of oxygen in healthy people, it suggests the lungs are transferring oxygen effectively, with no major issues.
Interesting. Okay. So let's talk now about ventilation perfusion mismatch and right to left shunt. How would these cause a raised AA gradient?
Ventilation perfusion, VQ mismatch, and right to left shunt both increase the AA gradient by reducing how much oxygen gets from the alveoli into the arterial blood. In VQ mismatch, some lung areas get more air than blood, or vice versa, like in COPD or pulmonary embolism, so oxygen transfer is inefficient, widening the gap between PaO2 and PaO2. A right to left shunt, like in certain heart defects, lets deoxygenated blood bypass the lungs entirely, directly lowering arterial oxygen and spiking the AA gradient.
Okay, now let's talk a bit about regional differences in ventilation. So in the lung, not all regions have the same ventilation. Explain why this is the case.
Regional differences in ventilation in the lungs happen because of gravity and lung structure. The lower parts of the lungs, closer to the diaphragm, get more air than the upper parts since gravity pulls blood and air downward, making the lower alveoli more compliant and better ventilated during breathing.
Okay. And so would hypoxemia be low partial arterial oxygen and high partial alveolar oxygen, or not necessarily?
Hypoxemia is low partial arterial oxygen, PaO2, typically below 80 millimeters, but it doesn't always mean high partial alveolar oxygen, PaO2. It depends on the cause, like in ventilation perfusion mismatch or shunts. PaO2 might be normal or high, but oxygen isn't reaching the blood efficiently, while in hypoventilation, both PaO2 and PaO2 could be low.
I want to spend a minute for us to talk about the history of gas exchange and transport in medicine.
In medicine, gas exchange and transport are critical for getting oxygen to tissues and removing carbon dioxide. Oxygen moves from the alveoli in the lungs into the blood via diffusion, binds to hemoglobin in red blood cells, and is pumped
I
by the
didn't
heart.
say summary, I said history. Tell us about when it started becoming an important topic, pioneers. I don't really even care about their names, but I do care about their work.
All right, let's dive into the history of gas exchange and transport in medicine, focusing on when it became a big deal and the key work done, without getting hung up on names. Way back, around the 6th century BC, people were already thinking about breathing as something vital, like a life force tied to the soul, but it was more philosophy than science. By the 2nd century AD, folks started piecing together ideas about how the heart and lungs work together, though their theories were pretty rough and mixed with guesses about blood and air. The real shift came during the Enlightenment, roughly the 1600s to 1800s, when scientific methods took off. People began using experiments and observations to understand the body, moving away from just speculating. In the 17th century, one key leap was figuring out that blood carried something vital from the lungs to the body. Experiments showed the air wasn't just cooling the body, it was doing something chemical. By the late 1600s, work with early devices like negative pressure ventilators started, helping people who couldn't breathe well, like those poisoned by gases. This was a hint that understanding how gases move in and out of the body was critical. Fast forward to the 18th and 19th centuries, and things got serious. Scientists nailed down that oxygen in the air is what keeps us going, not some mystical substance. They showed that oxygen gets into the blood through the lungs, and that carbon dioxide is a waste gas exhaled out. One big moment was proving that burning, oxidation, happens in the body's tissues, not the lungs, by comparing oxygen and CO2 levels in arterial versus venous blood. This flipped old ideas on their head. By the early 20th century, the focus sharpened on how gases move in the lungs. Around the 1900s, researchers started measuring blood gases more precisely, figuring out how oxygen and CO2 pressures drive diffusion across the alveolar walls. This led to better tools for analyzing blood, though they weren't widely used in hospitals yet. Work during this time also looked at why pilots were crashing due to low oxygen at high altitudes, which pushed studies on how the body handles oxygen shortages. In the mid-20th century, the math and physics of gas exchange got clearer. The alveolar gas equation we talked about earlier started taking shape over 60 years ago, giving doctors a way to calculate oxygen levels in the lungs and spot problems, like ventilation-perfusion mismatches. Studies also showed how the lung structure, like the huge surface area of alveoli, makes gas exchange super efficient. Around this time, devices like the iron lung, developed in the late 1920s, became famous for helping people breathe during things like polio outbreaks, showing how...
Okay, no, that's good enough. That's good enough. Well, okay, now, in 2 sentences, I want you to tell us, if you had to take away one thing from today's episode about gas exchange, what should we take away?
Gas exchange is all about getting oxygen into your blood and carbon dioxide out efficiently, driven by pressure differences in the lungs. Understanding it, through tools like the alveolar gas equation and AA gradient, helps doctors spot and fix problems when your body isn't getting enough oxygen.
Nice. Well, thanks for watching, guys. I'm trying to do these new type of videos where they're kind of 30 minutes long. Maybe that's gonna make them more watchable, maybe not, who knows, but that's what I'm going for anyway. Well, yeah, peace out. Thanks for watching.
Glad to help.